The second method is the two-phase method to find a starting basic feasible solution. Again, suppose we're looking at the problem minimize Cx subject to Ax equals b, x greater than or equal to 0, and there's no obvious basis to start with, in which case we change the original problem to a new problem, p prime, where the constraints are perturbed by a vector of artificial variables with x and xa greater than or equal to 0. So any feasible solution to p prime will be feasible to p if and only if xa is equal to 0. Other than that, there's, of course, ax will not be equal to b unless xa is equal to 0. So in this case, rather than perturbing the problem with Cx plus m times the artificial variables, as in the big M method, what we do is we simply minimize the sum of the artificial variables. In other words, the vector of 1s times xa, where E is a row vector. Well, let's just make it transpose here. Where E transpose is a row vector of 1s of appropriate size, so that this is simply adding up all of the artificial variables and you're trying to minimize this. This is your phase 1 problem. The phase 1 problem simply throws away the old objective function, has nothing to do with it. In fact, the original problem could be a maximization. The phase 1 problem is still a minimization, okay? Because you're trying to minimize the sum of the artificial variables, and that will, of course, eventually achieve 0 for each artificial variables if it is possible to do so. If it is not possible, of course, whatever you end up with. Okay. So the algorithm goes as follows. Solve phase 1 problem. The minimization of the artificial variables. If x sub a is equal to 0, all artificial variables are 0 at the end of phase 1, then a basic feasible solution to the original problem, as well as, of course, to p prime, is at hand. Continue to phase 2 with that basic feasible solution. And in phase 2, so this is phase 1. And in phase 2, what we do is we insert back the original objective function. Cx with minimization or maximization, whichever one might be the case, and begin with the basic feasible solution found at the end of phase 1. That's the main idea. Now, of course, phase 1 may also terminate with some artificial variables positive, even though you've reached optimality for the phase 1 problem. Not all of them are 0. In that case, what is the conclusion? So let me just write it here. If xa is not equal to 0 at the end of phase 1. Then we don't continue to phase 2. There's nothing to do. We just terminate the procedure because the original problem is infeasible. You simply stop with that conclusion. Okay? All right. We had an example that we worked out using the big M methods. So let me go through this example one more time. This is the same example. With 3 constraints, all in standard form. x4 is a slack variable, x3 is a surplus variable. All variables are non-negative. This is the actual or the original problem that you that you wish to solve. And the phase 1 problem has all the constraints except that the objective function is now different. We are changing it to, well, I'm going to add 2 artificial variables, one to the first constraint, the second one to the second constraint. And I'm going to also use x4 as a possible starting variable, okay, because it already has a unit vector. So you just add as many as you need. All right, so in this case, we're going to minimize the sum of x5 and x6, which are the artificial variables that are not in the original problem. The constraints are perturbed with those new variables. All variables are non-negative. And so this is my phase 1 problem, which is just about the same as the big M problem, except that the constraints are the same, except that in the big M method, your objective function had the original for x1 plus x2 plus m times x5 plus m times x6. That's what you had. Here, 4 and 1, the original coefficients are replaced by zeros, actually. That's what happened. And the other ones have coefficients of 1. That avoids inaccuracies or possible losses of precision due to keeping a track of a large number, m. Okay? All right, so here we begin with the following tableau. Let me just call this R. Okay? So we're minimizing R here. With initial basic variables x5, x6, and x1. Not x1, but x4. All right, so coefficients are, you're just taking this again as a row 0 here with r minus x5 minus x6, okay, equal to 0. And the other ones are 3, 4, 1, 1, 3, 2, 0, minus 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 0, 3, 6, 8. That's your set of equations. And of course, you want a 0 here and a 0 here. It's not in proper form. So all you have to do is add proper multiples of these artificial variables to the top row. In this case, of course, 1 times either row, or both rows actually. That will give you a revised version of the new row, which is going to have a 7 here, 4 here, minus 1. That one is still 0. This one becomes 0, 0. This becomes 3 plus 6 is 9. And the first one is, of course, always, it doesn't change. 0 plus 0 added to 1. Doesn't change. Okay, so now you can initiate your simplex method with the revised row 0. And this is a minimization, so we choose this one as my entering. And then, which is the smallest ratio here? This one is the smallest, right? So you pivot on that, and you get the new solution. So in this iteration, of course, going from the initial to the next tableau, I'm getting rid of one of the artificial variables. Your second tableau looks like the following. Okay. At this point, we choose x2 as the entering variable because of the positive reduced cost here. And then you look at the ratios, and it turns out that the second one is the smallest. So x6 will leave, x2 will become the new basic variable. Of course, as soon as x6 leaves, both artificial variables will have become 0. So in the new tableau, I know for sure that I have a basic feasible solution to the original problem, because x5 and x6 are both 0. So the new tableau. That's the new solution for the phase 1 problem. At this point, optimum is already reached. Optimum solution for phase 1. Because all reduced costs are less than or equal to 0 for a minimization. Okay? X5 and X6 are both 0, which means a basic feasible solution for P is available now. It is the one provided by the tableau. So we begin with that. Now I begin my phase 2. Now we revert back to the original objective function whose value is, say, z. Okay? We have the variables x1, x2, x3, and x4. The artificial variables, you don't need them any longer, so you just throw them away, and you have the right-hand side column. So my tableau is shrunk now. It's smaller. And we have the variables x1, x2, x4. My set of equations with x5, x6 columns dropped are simply 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. Let's just write down 1/5 minus 3 over 5 and 1 and 0, 0, 1 with 3/5, 6/5, and 1 on the right-hand side column. Sorry. I made a mistake, right? Did I make a mistake? No. Okay, these are thrown away. So, all right. So the objective function is now z equals 4x1 plus x2, which means z equals, or z minus 4x1 minus x2, the other ones have 0 coefficient, is equal to 0. That's what you have for row 0. Again, we need to revise this because your reduced costs are supposed to be 0 here. You can compute it using the formula that I gave you. Reduced costs are what? CBB inverse times the column AJ minus CJ. And if you don't want to bother with that, you can just add appropriate multiples again. In this case, we want a plus 4 here, I guess, right? Oh, they are both minus, sorry. This is a minus also, right? And this one is plus 1. So when you do that, you get 0, 0. For this one, you get 4/5 minus 3/5, which is 1/5. This one is still 0. This one is 12/5 plus 6/5, 18/5. That's how much you have. And then you minimize or maximize. Which one? Minimize, yeah. Be careful. You know, whatever the original optimization is, that's what you do. So in this case, we minimize, and we enter that one due to plus 1/5 here. And then you look at the ratios. I don't know which one is smaller here. Is it this one? Yeah. So you pivot on that, and that should get you to the optimal solution, I hope. So you now have the optimum basic feasible solution to the original problem P. Quite straightforward, actually. However, there may be some complications, as is the case with anything else. So let's look at how we can handle complications. So phase 1 either terminates with all artificial variables equal to 0 or sometimes not equal to 0. Okay? If it is the other case, if xa at the end of phase 1 is not equal to 0, that means, of course, the objective value of the phase 1 problem is positive, because there's at least one artificial variable at a positive level. In this case, we stop. No feasible solution to the original problem P. Now, when phase 1 terminates with xa equal to 0, there are two possibilities. Either all artificial variables are non-basic, which is the good case, or some of the artificial variables are 0, but they are still basic. Okay? So, this is the case that has occurred in the example problem. And in this case, we simply continue to phase 2. Begin with the basic feasible solution found at the end of phase 1 by throwing away all artificial variables. Okay? You simply discard them. In the second case, or in the case where some means at least one, okay? Some artificial variables are basic, but 0, okay? So we're talking about a degenerate basic feasible solution containing some of the artificial variables. In this case, to continue to phase 2, you want to get rid of the artificial variables. So you need to know how to handle that situation, okay? And I'm going to simply write down here what we should do, then I'll illustrate it or describe it in a general tableau. Discard artificial variables using the equations of the final tableau or the terminating tableau of phase 1. Okay, so the explanation of this statement is here. I need to draw a large tableau here because otherwise, we can't really explain it. So suppose we have x1 up to xk. These are the original or the legitimate variables, xk plus 1 up to xn. These are the legitimate means here the variables that belong to the or that come from the original problem. Okay, assume that the original problem has n variables. Some of them will be basic, the other ones will be non-basic. That's how I partitioned here. So the legitimate basic variables are the first k of them. And then we have the legitimate non-basic variables. Xk plus 1 up to xn. Then we have xn plus 1 up to, what is that? Whatever. X xn plus k, yeah. xn plus k. And then we have xn plus k plus 1 up to the last one. These are artificial non-basic variables. And these are the artificial basic variables. Then, of course, you have the artificial R column here, which is nothing but a decoration, except that these are systems of equations, so I keep them there. Okay. Now, the basic variables listed here are x1 through xk, and then xn plus 1, xn plus k plus 1 up to the last one. Legitimate basic variables and artificial basic variables. Of course, I'm assuming here that we index things in this way so that we can represent everything in an orderly fashion. Okay? They don't have to come in this particular order, actually. Okay. Now, what am I supposed to have here in row 0? You've got zeros for your basic variables. The right side is also 0 because all artificial variables are by assumption 0. Well, that's how we terminate it. Okay? Now, we've got our unit vectors here. Okay? So there's a big identity here, k by k identity. You also have identity here. Okay. What do you have here? We've got 0. And over here, you also have zeros. The right sides for the legitimate variables are whatever they are. They're basic. Okay? The right sides for the artificial basic variables are by assumption 0. That's the case we're looking at. They are basic, but they are 0. Over here, we've got the reduced costs. And we've got, non-zero, or we've got some matrices, say R1, R2, R3, and R4, whatever they are. Okay. Okay. So what you do is, let me have your attention here. What you do is, you're trying to replace the artificial basic variables with legitimate variables that are currently non-basic. So you want to replace all these, how many of them? N minus k of them, m minus k of them. There are m minus k such variables here. You want to somehow pick m minus k non-basic variables from the legitimate set of variables and replace these by them. To do so, all you have to do is look for non-zero elements in R2 on which you can pivot. Okay? So, if I, for example, look at the first, or suppose I located a non-zero element here, say in the first row and in the first column of the legitimate non-basic variables, you can pivot on that. All you do is you enter the non-basic variable and exit the one under consideration and just make that replacement one at a time. So as long as you have non-zero numbers here, which could be negative actually, or positive, you can always do your pivoting operations to replace these. So pivot on, you will do this one at a time, of course. Okay? You will replace one of the artificial basic variables with a legitimate non-basic variable. Then you will obtain the same situation with a smaller number of artificial basic variables now. You apply the same reasoning. You find a non-zero number in R2. You do one more pivoting. You just keep doing this. So pivot on a non-zero element of R2 to replace an artificial basic variable with a legitimate non-basic variable. Do this repeatedly until one of two things can occur. One of them is the desirable outcome. You do this one at a time, and finally all artificial variables are removed from the basic set and replaced by sufficient number of legitimate non-basic variables. That's one possibility. So, until either all artificial variables are replaced by legitimate variables that used to be non-basic, which become basic now, okay? Or what is the or part?
No possible non-zero increase.
Say that again?
No possible non-zero increase.
Exactly. Or the most recent version of R2, the one you obtained through these repetitions, has no non-zero entry in it. Okay? So, of course, when you have no non-zero entries in R2, you cannot really pivot any longer. So suppose we got to that situation. Suppose there's a big 0 here. What does that tell you? Does it tell you anything? No. It tells you the following. This is a system of equations. See, remember that always. And you've got all the legitimate variables having coefficients of 0 here. So in this set of equations. Then you've got artificial variables with non-zero coefficients, but they are all 0. They are non-basic. And then you've got other artificial variables that have coefficients of 1 in exactly one of these equations, but they're also 0. So this set of equations are certainly, that's a redundant set of equations. It has nothing to do with the original problem. Okay? So in the latter case, so in the latter case, when R2 becomes 0, the surviving set of equations, whatever is left in the lower portion of the tableau, they are redundant, so you just drop them. And continue to phase 2. Okay? Does that make sense? Okay. I'm not going to give you an example on that, but if you happen to run across to it in the exam or somewhere, you know what to do. Any questions on the two-phase method? All is fine, huh?